Silvia?
No, io parlo forte.
Ah, tu parli forte. Magari mi sentite anche senza microfono. Allora non lo uso. I'm very happy to welcome you here for our Frontiers in Chemistry seminar. Also on behalf of our director, Professor Maggini, who is unfortunately kept in Rome by some mysterious bureaucratic affair that I don't know much about. He would have liked to be here, of course, but it was not possible. Before leaving the stage to Professor Gross, who will introduce our guest, Dr. Philip Ball, let me just say that this is a very interesting seminar which tries, in my opinion, to widen a little bit our usual landscape, which is usually very technical, very specialistic, and instead it tries to remind us of what is really the matter of what we do, that is the beauty of our science, which is something that maybe sometime we tend to forget. So before I say anything else, I leave the word to Professor Gross, who will introduce our guest.
Grazie Nino. Buonasera a tutti, good morning to everybody. So it's a pleasure to introduce once again Dr. Philip Ball. Dr. Philip Ball was a guest at the University of Padua for the Aqua Conference, in which he gave an outstanding talk on water-aware molecules, explaining also to non-specialized, non-chemist attendees the peculiar properties of water. So Philip Ball is one of the most important science writers in the field of chemistry, but not only of chemistry. He holds a bachelor in chemistry from the University of Oxford and a PhD in physics from the University of Bristol. He worked previously at Nature for over 20 years, first as an editor for physical science and then as a consultant editor. His writing on science for the popular press have covered topical issues ranging from cosmology to the future of molecular biology. He still writes regularly for Nature, but he has contributed also to publication regarding realization of science, ranging from the New Scientist to the New York Times, the Guardian, the Financial Times, New Statesman, and he's still collaborating with the Chemistry World, the well-known chemistry blog, Nature Material, and for the Italian science magazine Sapere. He has authored extremely beautiful books on chemistry, elements, water, and biography, which I really warmly suggest you to read because they are really nice insight into our science. And today, Philip was coming back from the conference, but he was willing to provide us with a talk for chemists. Thank you very much.
Thank you, Sylvia, and thank you for the invitation. It's really nice to be able to give this while I'm here. I know that I'm preaching to the converted today, of course, but you know, I guess I feel sometimes there are two types of people. There are those for whom would it be good if I use this? Would that help? Yeah. Okay. Oh, there we go. There's an attachment. Yeah, so, oh, that's better. So I know there are some people for whom an image like this sends them sort of running for cover, and there are some like us who have the opposite response, I'm sure. And to me, there's just something irresistible about these sorts of images, and I think it sort of shows what drew me first to chemistry, which was the stuff itself, the colored powders, the pungent smells, you know, ammonia and sulfur dioxide, not all of them nice, but all of them memorable, the explosions even. I suspect that my experiences were fairly typical for someone who learnt chemistry long ago, long enough ago, that it was possible for it still to be given a sense of danger. So I was delighted to discover when I was at school that it was possible to make a touch-sensitive explosive with ingredients that I could just steal from school. I'm talking about nitrogen triiodide, which I imagine some of you will know. You just make it by mixing ammonia with iodine, and you dry it on the filter paper, and then you have this stuff that detonates when you touch it with a sort of cloud, a puff of iodine vapor. And I remember being allowed in one lesson at school to stick a finger into a bowl of mercury. And I imagine today there are people who haven't been able to do this. I think everyone should be able to do this because you won't forget it. I haven't forgotten that cold, unearthly fluid that I felt that was kind of glistening. It felt impossibly dense. You put your finger in and took it out and it was dry. It was the most unearthly stuff. None of this, I'm sad to say, matches the kind of home experimentation that Oliver Sacks, the neuroscientist and neurologist, was able to do as a boy in the little lab that he set up in his family home, in the laundry room. Oliver's father was a pharmacist, and so getting hold of the ingredients wasn't difficult for him. And he made chemical gardens, so these kinds of things from silicate solutions. This is actually an image from the book that I'm really talking about, called The Beauty of Chemistry. He tried to extract metals from their ores. He made ammonium dichromate volcanoes, and I was delighted to discover he did make nitrogen triiodide too. Now, he says the room that led out onto his garden, he said, was the room that he did these experiments in led out directly onto his garden. And so he says that if I concocted something that caught fire or boiled over or emitted noxious fumes, I could rush outside with it and fling it on the lawn. The lawn soon developed charred and discoloured patches, but this, my parents felt, was a small price to pay for their safety. My own too, perhaps. And in those days, it was possible for someone for a young person like Oliver Sacks to just go along to a chemical supplier on your regular street and buy things like a lump of sodium, which he and his friends then went to the local ponds to throw in to see what would happen. And all of this is described in this book, which I imagine some of you will be familiar with. It's Oliver's memoir, a chemical memoir really, called Uncle Tungsten. And I think it's the best testament ever written to the fact that there is no field of science that works more on the senses than chemistry does. The Nobel laureate Robert Woodward put it this way. He said, "It is the sensuous element which plays so large a role in my attraction to chemistry. I love crystals, the beauty of their form and their formation, liquids, dormant, distilling, sloshing, swirling, the fumes, the odors, good and bad, the rainbow of colors, the gleaming vessels of every size, shape and purpose. Much as I might think about chemistry, it would not exist for me without these physical, visual, tangible, sensuous things." And I've seen nothing that better captures these aspects of chemistry than the astonishing videos made by Liang and Wenting Zhu for their Envisioning Chemistry project. Several years ago, I was at a conference in Shanghai, and Yan got in touch with me. I'd not come across him before, and he jumped on a train from Beijing down to Shanghai to talk about the possibility of our collaborating. And that was really my introduction to his work. And so, I was delighted and entranced by it. And so I told him I'd be happy to do that if the opportunity arose. And then some years later, he got in touch and said, well, we're writing this book for MIT Press, or at least we're providing the pictures for it. Could you write the text? So I happily said yes, and this was the result. So this is, as I say, published by MIT Press the year before last now, I guess, 2021. And it's filled with amazing images of chemical processes like these, from crystal growth to bubble formation, from precipitation to color changes. And I hope that we've been able to reach beyond the stinks and the bangs that appealed so much to me when I was younger, and to show that there is a much more profoundly aesthetic aspect to chemistry that I think is unequaled among the sciences. Yen's work has been used by chemists all around the world, and you can see why, I think. It featured in the opening ceremony, yes, I've got it here, the opening ceremony for the International Year of the Periodic Table in Paris in 2019. And in all honesty, it was hard to capture in still images the wondrousness of the videos that Yen and Wenting have made, which I think is a reflection of how the beauty of chemistry is often a dynamic beauty, both at the everyday scale and at the microscopic and the molecular scale. And I want to try to show you some of that work, some of the videos too. And I'm a little bit nervous here because I'm not used to this computer or this touchpad, but I think, yeah, there we go. Oh, what am I doing? Okay, right. Let's see if I can get this running. I'd like to full screen it, but I don't think I want to risk that. This does have music to it, which I'm afraid you're not going to hear. But I just want to let this run for a bit to give a sense of what this was all about and what drew me to collaborate with Yen and Wenting. And I think, as you watch this, I think it's clear. What sort of strikes me is that these are all kind of familiar processes and images. It's really kind of high school chemistry, but the skill with which they have managed to capture these processes is, it's not to be taken for granted. There's a lot more skill, technical skill, and artistry to this than is available to anyone. I want to at least let it get on to the crystal growth. Although, I mean, quite how he gets these shapes, I don't know. And I know that it involves a lot of work and a lot of experimentation. Oh, yeah, if you can get there. But I don't think we've got a link, Sylvia, to the... I guess we'd need an audio lead. Oh, here we go. So this is the crystal growth. Oh, lovely. Okay, yeah. So full screen is nicer. Thank you. There it goes. Okay, yeah, so I think that's, oh, this is a nice one too. Let's have this one. I'll keep saying that for the rest of the video, but it's just mesmerizing, really. All right, I'll see if I can get back out, get back to the presentation. And yeah, there we go. Lovely, thanks. So this astonishing beauty that resides in chemical products and processes, I think too often passes unseen, or at least unacknowledged as being chemical in nature. So, you know, we can marvel at the delicacy of a snowflake or the rich brightness of a flower and at its smell, its fragrance, while failing to realize that chemistry is at work here every bit as much as it is in pharmaceutical plants and oil refineries. And I make no apologies for using this slippery word, beauty, in the title of the book, but I want to acknowledge that actually that's a complicated word when used in this context. And I had to wrestle with what beauty really sort of meant in this context. When I wrote this book, it must be 15, 16 years ago now, for the Royal Society of Chemistry, where I tried to sort of explore and maybe push back a little on notions of beauty in science. Now, I wrote this because the Royal Society of Chemistry in the UK asked me to pick what I considered to be the 10 most beautiful experiments in chemistry. And I'll just briefly show you the list that I came up with. I'm not going to go through them by any means. But it was clear to me at once that what might qualify an experiment as beautiful was not necessarily the same as what might make a molecule considered beautiful, for example. And that's different again from the notion of beauty that physicists often talk about when they're talking about equations or theories. All of them tend to be very different from what beauty is thought to mean when it's brought up in a discussion of art or aesthetics. In fact, that word has largely been banished from art for some time. And I think not without good reason, because artists and art theorists are rightly skeptical about the idea that the purpose of art is to be beautiful, to be decorative. In other words, there's a lot of baggage associated with this idea of beauty. If you ask a chemist what qualifies as a beautiful molecule, you're likely to get an answer like this. And this is, in fact, it was in the title of Hugh Aldersley Williams' very good book on the discovery of C60, which, you know, it's considered beautiful because it has this polyhedral, very symmetrical shape. So in other words, I think chemists on the whole tend to be Platonists. They find beauty in symmetry. And maybe so, but that doesn't really make a connection then between ideas of beauty in aesthetic theory. For Plato himself, art was actually too messy to be truly beautiful. And for Immanuel Kant, beauty, he said, depends on a departure from strict regularity and perfection. As Kant put it, all stiff regularity, such as approximates to mathematical regularity, has something in it repugnant to the taste. Francis Bacon, the 17th century English philosopher, seemed to agree. He said, "There is no excellent beauty that has not some strangeness in the proportion." But I would defend our use of beauty in this context in our book for that very reason. For one thing, Yen and Wenting's imagery says to me that beauty is indeed in the eye of the beholder, not in the sense that it's just all a matter of personal taste, but because it depends on how you look. What's wonderful in their videos and their photos is not necessarily intrinsic to the processes that they're showing. It comes from their skill, both their technical skill, but I think also their artistic skill in determining how we see it. I think it's immediately apparent that their imagery that I showed you isn't something you can just casually do with a smartphone. Their images are carefully composed and selected and captured with great virtuosity, just as they are for the best photographers. This is what I appreciate so much about their work, because in my view, their work helps to instruct us about how to look and how to see, which of course then really does connect to theories of art. You see, I mean, I've conducted, oh, there's Immanuel Kant's view on beauty. I've conducted precipitation reactions. I'm sure you have before, but they've never quite looked like this before. And I think that perhaps it's here that art and science really find some common ground, because they are both concerned, first of all, with revealing to us things that we might not immediately notice. They show us what is really there. And so they demand a special kind of engagement with the world beyond the superficiality of our daily routines and our everyday experience. They ask us, both art and science, ask us to really attend to the world. And that, I think, is where science itself really begins, with noticing, with attending. Here I have to invoke Leonardo, because noticing and attending is the key to everything he did. I mean, we've just had this wonderful meeting on water, and when Leonardo looked at the flow of water, as he very often did, what he was trying to discern was the deep patterns and the forms that are beyond, that lie beyond the sort of superficial play of light on surfaces. His sketches like this don't actually look very much like what we really see. They're his attempts to go beyond that, to look at the underlying patterns that he discerned. And I can't help but be struck by, particularly given the way that kind of East met West in our book, I can't help but be struck by how similar this kind of way of depicting flow is to the way that it is often done in East Asian art, where again, flow structures have been depicted in ways that try to capture the complex, organic, really, forms that underlie the flow, rather than just a sort of an instantaneous photographic type reproduction. And isn't this what so much of science is about as well? This kind of idealization, this capture of the deeper patterns beneath what we see. And to that end, science creates new tools for seeking beneath the surface, for stopping time, for magnifying space to capture what the eye can't see. Even the high-speed photography invented in the late 19th century, when it was used by experts like Harold Edgerton at MIT, he used it to show us patterns and wonders, I think, in nature that we'd never been able to notice before. You know, you couldn't see this. It's too far, it's too quick, too ephemeral to see with the naked eye. This particular image serves as the frontispiece to the 1942 revised edition of Darcy Wentworth Thompson's classic book on growth and form, which explored how structure and order and pattern appear across the scientific disciplines according to some universal principles as he saw it. And I'd like to think that our book shares something of the same spirit in its own modest way as this. We look, for example, at some of the amazing patterns that emerge during crystal growth and some of the chemical reactions that are known to generate complex patterns, like of course, the Belousov-Zhabotinsky reaction. Just the kind of processes that Darcy Thompson discussed, although at that point, he originally wrote the book in 1919, at that point there wasn't really any fundamental understanding of what lay behind these sorts of patterns. It always amuses me that On Growth and Form begins with this statement. So Darcy Thompson says, of the chemistry of his day and generation, Kant, again, declared that it was a science, but not science with a capital S. For the criterion of true science lay in its relation to mathematics. So it rather seemed that Darcy Thompson felt that the chemistry of his day still hadn't quite attained the status of a true science. And we can argue about whether it's done so now, but I think we can argue about whether mathematization should in any case be the ultimate criterion for what qualifies as science. What our book, The Beauty of Chemistry, aims to do is to return I think, to the real roots of that enterprise, of that chemical enterprise, by revealing the truth in what the 19th century chemist and astronomer John Herschel once said. Sorry, that's Darcy Thompson. So this was what Herschel had to say. To the natural philosopher, there is no natural object unimportant or trifling. A soap bubble, an apple, a pebble. He walks in the midst of wonders. And here are some bubbles photographed by Yen and Wenting, just the kind of thing that, you know, we can see regularly in carbonated drinks and champagne. It's, again, a totally familiar phenomenon, but one that, when we attend closely, becomes utterly beguiling and full of questions. Why, for example, do these little bubbles take these wiggling paths as they ascend? What determines the bubble size? How are they nucleated? And this is precisely why I say that science doesn't, as sometimes people will say, it doesn't de-enchant the world. On the contrary, it re-enchants. It requires a willingness to find strangeness and surprise in the mundane, in the everyday. And once you start asking questions about things like this, then you'll find there's no end to them. You'll never exhaust the questions. For example, we've admired flowers since ancient times, of course, but there are still plenty of gaps in our understanding of how the colors of flowers are formed, let alone what purpose they serve in evolution. Yen and Wenting have produced some lovely images of the colors of flowers and how they can be changed by chemically treating the petals. And I talk about, in the book, about what we understand about these colors and the pigments that produce them. And I show that sometimes nature arranges the pigment molecules in wonderful, I think I've got here, did I manage to find? Yes, wonderful supramolecular structures like these that are presumably delicately tuned by evolution, although for what reason, we don't really know. In other words, chemists are still finding the unexpected in what seem to be the familiar objects, bubbles, flowers, even a water molecule, as we've been hearing again. And the fact is that all of these studies, all of these questions begin in experience, in what we can see and hear, feel and smell, in our concrete reality and the way that it invites our attention and our appreciation. And I'll admit that I have an agenda with this book, and I think there's an agenda really in Yen and Wenting's work as well, which is to rehabilitate the status of chemistry from the common perception in the public sphere that it's, at best, it's a kind of slightly old-fashioned and sleepy science, and at worst, it's a dirty, polluting business. The age of John Herschel is more or less the one that's described in this book by Richard Holmes, The Age of Wonder. It's a wonderful book, when chemistry was seen very differently. In that time, in the early 19th century, or the late 18th century, at that time, it was the preeminent romantic science. It was a bridge between the scientist and the poet. This was the time, as Richard explains in his book, this was the time that Samuel Coleridge, the English poet, would go to the Royal Institution to hear Humphrey Davy lecture in order, Coleridge said, in order to replenish his stock of metaphors, to find things he could use in his poetry. And Davy would return the compliment. Humphrey Davy composed poems himself. Not terribly good ones, but, you know, they could be worse. And thanks to the flair and the passion of people like Davy, chemistry then captured the public imagination. Sometimes, it's true, in ways that Davy himself might not have been so happy with. So there was this famous cartoon by James Gilray of Davy's lectures on laughing gas at the Royal Institution. But chemistry then seemed to be the science that was most likely to reveal the mysteries of nature, just as Mary Shelley, whose father knew Davy and who might herself, as a young girl, have attended Davy's lectures at the Royal Institution. She tells us this in Frankenstein. John Herschel was himself a dabbler, well, really more than a dabbler, I should say, in chemistry. He was a pioneer of photographic imaging, and his discovery of how to fix silver using sodium hyposulfite was what allowed William Fox Talbot and Louis Daguerre to develop the craft of photography. Herschel was also the inventor of the technique known as blueprint or cyanotype, which was used, I'm constantly jumping ahead of myself. So here is what Mary Shelley had her character, Professor Waldman, say in Frankenstein. So John Herschel was the inventor of this technique, of the cyanotype, and it was used by Anna Atkins at the same time in the 19th century to make images of plants that are now regarded both as botanical studies and images of real artistic quality, dissolving the boundaries between the arts and the sciences. All of this gave 19th century chemistry a kind of cultural status and allure that seems far removed from the way it's regarded today. And it was, I think, an allure bound up with notions of craft, with science as a form not just of understanding, but also of making things. It was in the 19th century that chemists began to understand the transformations that they, and in earlier times, the alchemists, had been making for centuries, to understand them as rearrangements of atoms and of sculpting of molecules into particular shapes. And chemists, I think, today display the greatest creativity within the sciences, the greatest urge to make new things. Today, chemists are truly designers of atoms, figuring out how to arrange them into new unions with useful shapes and useful properties, or perhaps just because of the joy of it, just because of the beauty of what they can make. And here, many chemists are, of course, inspired by nature, which the Nobel laureate Francis Arnold, now a science advisor to the Biden administration, I got people like Francis to give us a few quotes for our book, and she was happily obliged. So she said that nature is a brilliant chemist and by far the best engineer of all time. And, you know, as an illustration of that, how about this? This is the bacterial flagella motor. It's a genuine motor that you really have to call it that. It's just 26 nanometers across. And it's embedded in the membrane of bacteria and whirls around several hundred times a second, propelling these sort of corkscrew-like flagella that propel the bacteria through a liquid so that they can go towards sources of food. This was an image that was obtained from electron microscopy by a group at Zhejiang University in China, just, I think, a couple of years ago. And it's hard to believe, I think, but nevertheless, it's evidently true that natural selection could generate something so exquisitely engineered as this. So it's no wonder, then, that Francis Arnold went on to say this. She said, "I'm among the many inspired by the beauty and remarkable capabilities of living systems, the breathtaking range of chemical transformations they have invented. The complexity and myriad roles of the products. I am in awe of the exquisite specificity and efficiency with which nature assembles these materials from simple, abundant, and renewable starting materials. Nature assembles atoms, of course, into proteins, into DNA, and from these constructs cells and organisms. And in doing so, it achieves the astonishing and yet to be understood feat of making matter aware of itself." I mean, put like that, it sounds like a kind of poetic metaphor, right? But actually it really isn't. It's just a simple statement of fact. That's what has happened, and we should never forget to be amazed at that. Nature's exquisite chemistry allows parts of the universe to become conscious. And we humans, of course, are far less adept at molecular construction, but we're getting better. Frances herself has shown one way of doing that by finding ways of producing a kind of directed evolution, an unnatural selection in the test tube by which she can make molecules like nature's own that can perform tasks not found in nature. And this is, it's not going to be very visible on this. This has been translated from Mac. Now you can see why. But this is a good place to look for more information about the directed evolution that Francis Arnold is doing. In his novel, The Wrench, at least that's the English title, Primo Levi drew an explicit analogy between the profession of the construction engineer who makes bridges and the synthetic chemist who makes molecules. Incidentally, I was surprised actually to hear that in Italy, sometimes you're surprised that Primo Levi is as well known outside of Italy as he is here. I mean, it should be no surprise. I mean, maybe I'm biased because I'm a chemist, but or was a chemist, but really, you know, Primo Levi is clearly one of the most important authors of the 20th century. So he really is well known. He's of course best known perhaps for his book, The Periodic Table, but also for his testimony of the Holocaust, If This Is a Man. Anyway, Primo Levi says in The Wrench, so there's this construction engineer and a synthetic chemist representing Levi, I think, talking. And the novel's narrator is the chemist. And he tries to describe to the engineer why their jobs have so much in common. And he says this, he says, my profession, the profession I studied in school and that has kept me alive so far, is the profession of the chemist. It's a bit like yours, only we rig and dismantle very tiny constructions. The things we handle are too small to be seen, even with the most powerful microscopes. So we've invented various intelligent gadgets to recognize them without seeing them. But we are still blind, even in the best circumstances. That is, with structures that are simple and stable. Blind, and we don't have those tweezers we often dream of at night, the way a thirsty man dreams of springs, that would allow us to pick up a segment, hold it firm and straight, and paste it in the right direction on the segment that has already been assembled. If we had those tweezers, and it's possible that someday we will, we would have managed to create some lovely things that so far only the Almighty has made. For example, to assemble perhaps not a frog or a dragonfly, but at least a microbe, or the mold, or the spore of a mold. I didn't know that quote from Levi when almost 3 decades later I wrote this piece for Nature. So this is from 1995. It was written about, it's a conference report of a conference we all arranged on complex molecular systems, as we called it then. But I took my title from what the Harvard chemist George Whiteside said at the meeting. He posed this challenge: can we harness and control molecular complexity well enough to make a synthetic dragonfly? Okay, so 28, 29 years later, we're not there yet, but we've come a long way. We have the tools that can act like Levy's tweezers, which can let us pick up individual atoms and place them where we want them to. That was shown actually also around the same time in the mid-1990s, and we had Don Eigler who made this image also at the conference. But we can also use these molecular scale tweezers to tie knots in molecules, and even to assemble individual molecules by pushing and prodding the components into place. And this is recent work by Leo Gross at IBM and his colleagues. Instruments like this can now show us single molecules like these, and, you know, amazingly, they're revealed just like the kind of schematic diagrams that chemists have been drawing since the 19th century. And chemists have become accomplished at harnessing the principles of chemistry to make complex molecular assemblies, like this one that we show. We have an appendix in the book that shows some of the molecules. So that's the only bit where they're not real photos, but we thought it was worth doing that. And this is one of them. This is the interlinked rings of a catenane. And it was work like this that another of our book's contributors, Fraser Stoddart, the 2016 Nobel Prize in Chemistry, alongside Jean-Pierre Sauvage, who makes knotted molecules, and Ben Feringa, who has figured out how to fashion molecular assemblies like these into very simple forms of molecular motors. I think I've got, yeah, so there's Jean-Pierre, there's Ben. And I think Ben will admit that our artificial motors, the ones he's made so far, don't quite have the elegance and the sophistication of the bacterial flagella motor, but we're still learning. And I know that, that Fraser and Jean-Pierre and Ben all find motivation for their work in the aesthetic response that it invokes. And this is what Fraser said in our book. He said, one of the really beautiful hallmarks of chemistry is its ability to keep reinventing itself over and over again. This endearing virtue places the chemist in the same arena as the painter, sculptor, or musical composer. The unique challenge for the chemist is that molecular beauty isn't something we can see directly, not at least without those special microscopes and other instruments that now reveal the molecular world. But what we might find there can amaze us. And Fraser says that, have I got, no, I haven't got him saying this. Fraser says that in many ways, small is more beautiful than we might expect at first glance. And I couldn't resist quoting too from the introduction that Ben Feringa provided to the Dutch edition of this other book that I published in the same year, which is an illustrated history of the discovery of the elements. And it's a bit of advertising, but I think also Ben's words testify to the allure of beauty in exciting the imagination and sparking the interest of young people in chemistry. So I'll just leave this here for you to read yourself. To my mind, Yen and Wenting's images and videos are a bridge to that beauty, showing us that if we can learn to look in the right way, it can conjure up wonders at everyday scales and in everyday settings, wonders like these. And I hope that our book will inspire you, as well as non-chemists, to think about the chemical world in a new way, as one of the wonders of nature, filled with artistry and inventiveness and dynamism and, yes, and beauty. Thank you. I don't have a full answer to that, but I do think that one strategy is to actually embrace and acknowledge how broad chemistry is. You know, it's the complaint we hear year after year, right, with the Nobel Prizes. Oh, it's another biology prize for chemistry. But it's not. It's not. It really isn't. That is, I think it's a good thing, you know, that those prizes show just how broad chemistry is. So, I think the fact that, chemical biology has become a thing and so much of chemistry that gets recognized, sounds like biology. I think that just is a recognition that we've got to the stage in chemistry where you can talk clearly and systematically about these biological systems that previously were just too mysterious and messy to study and to understand. So, I think I do regard it as a good thing, provided that chemists can seize the opportunity to really say, yes, this is chemistry. That's the point. This is chemistry that's expanding. Just as people like Fraser Stoddart and Ben Feringa and Jean-Pierre, the whole area of supramolecular chemistry was in some ways the beginning of that, of chemistry literally beyond the molecule. And that's where chemistry is going. We can build these amazing arrays out of DNA now. We can use DNA as a programmable, as a kind of informed matter, is how Jean-Marie Lane talked about it back in the 80s and 90s. That is what DNA for a chemist can now be and is. So I think that's certainly one strategy. I mean, in the physics direction, I guess when you see things like the STM being used and the AFM being used to push molecules around and arrange them, and that sort of came out of physics. It came out of the IBM physics labs. But again, it's the reason that's kind of getting attention is because it gives us those tweezers that Primo Levi was talking about. It's a chemical tool, and people like Leo Gross are really showing that it's a chemical tool that we can use it not just to make molecules, but to investigate, in real time, the progress of a chemical reaction. So I think, again, it's a good thing because it shows where chemistry has got to. So I think, in both of those ways, that's a good thing. But I think there's also the sort of broader message of just making it clear to people how much is chemistry that we just take for granted. The growing of a flower, the formation of the bubbling of a liquid. That's sort of what chemistry also has in its favor that physics doesn't have, the everyday nature of it. And what the challenge really is to show people that just because it's familiar and it's not talking about the Big Bang or dark matter or something, that doesn't mean that it's any less amazing and wonderful. And so I think that should be one of the objectives of chemistry, to recapture the everyday as a source of wonder.
Examples of other senses that can show the beauty of chemistry, like in sound or touch or feel, like flavors or smells. Would that be something to consider, or maybe you have done that already?
Yeah, I mean, absolutely. Smells and taste. There is, Hervé Thies is a chemist who, uses it in gastronomy. So he has in fact, he writes also a column for Sapere. I think that's fantastic because that again is, it's something that we all experience. It's an everyday thing, and it's about chemistry, and we're starting to get to the point, for example, where people are talking about designing new smells, that we understand the molecular basis of the olfactory system. We're getting to the point where we understand it well enough that we might be able to do that systematically. I mean, it's incredibly, surprisingly difficult to understand how olfaction works, but there are people, particularly using machine learning, who are thinking, maybe we can do that. Maybe you can design smells to order. The whole question of the relationship between a smell and chemical structure is still surprisingly mysterious. So there's a nice mystery there, but it's also one that connects to things that are very familiar to us. So yeah, I mean, I'd love to see chemistry, pushed more in that direction of how we can use those experiences. I mean, people have sort of said, or maybe with our book, we should have had a sort of scratch and sniff, thing for chemistry as well. I mean, I guess for me, if I think back to, it's going back actually to the late 70s, early 80s of my chemical training in Oxford, and the smell of the laboratory is what I remember. It's the Proust thing, right? That as soon as I smell some kind of benzyl compound, I'm back there in the lab. Smell too has this incredible direct route to our emotions and our memories and so on, that I think chemistry could utilize. But also touch, actually. I mean, I talked about touching mercury, but we now have, and I've used one of these haptic interfaces with an AFM, so that you can actually sort of feel as you go across. You feel the pumps of the atoms, which is pretty freaky. But those things are possible too. So I think there's still lots that could be done with the other senses. Yeah.
So by the way, I'm one of the chemists complaining every year as a student. Quite to witness that another Nobel Prize for biologist. No, you were commenting, you were hinting at the very beginning on the role of symmetry and the relationship between symmetry and beauty, and in the amazing picture you have shown in the video, there is can you a little comment on symmetry, beauty?
Yeah, I mean, I often find, several years ago, I spoke to Fraser Stoddart and one or two others, and Jean-Marie Lane actually, about trying to I wanted to try to engage chemists in a kind of molecular sculpture of thinking, why not use chemistry as a sculptural medium? We have the tools to do it now. Wouldn't that be fantastic? And then you have the interesting problem of thinking how to represent it. And but I quite quickly found that if you talk to chemists about making something sort of from an artistic point of view, they start to think about making symmetric molecules. And I didn't want that. I would have wanted, I don't know, to make a new form of hemoglobin that has, that has a different color, or something that makes us think rather than simply, look at a symmetrical object. So I personally, and I know many chemists feel differently, I personally don't really have that aesthetic response to just a symmetrical molecule. I sort of understand the idea, but it's not actually what we look for in art. There are people who say, well, there are these, symmetries and these hidden patterns and so on, but actually you have to look quite hard in art to find that. And what we tend to respond to in art is other things. The same is true in music. People say, oh, it's mathematical, there are mathematical patterns. But if you have too much of that, then I agree with Kant. It becomes boring. Actually, it's the violation of symmetry, the things that are slightly off-center, things that are slightly askew. That's what excites our interest visually. Yeah, I guess I'm skeptical about sometimes the excitement that chemists... I mean, I can understand, why making a symmetric molecule is a nice challenge, but it doesn't excite me in the way that other aspects of chemistry do.
I would again warmly thank Philip for his generous... He came to Padova after having asked him. He always was available to do everything we imposed to him in these days.
Oh, it's a pleasure. Thank you for asking.
And so thank you very much, Philip. And Philip will leave at 3:45. So if any one of you would like to speak with him half an hour, then at 4 I will bring him to Largo Meneghetti. He will be picked up and brought to the airport. But if you want, he's half an hour available. If you want to drink something or something. So,
sure.
Is anyone interested?
you. Thank you.
Would you like to bring something?
Maybe actually, yes. After that would be good. Thank you. Oh yes, let's take that off.
Let me take it.
Yeah, no.
Thank you.
Don't walk away with that otherwise.
Thank you.